the academic. You can have exposure to every other things.
Exactly,
Yes,
sir. Sir, we are not developing means in any field. We are just sitting and
Yeah.
It is
yes, sir.
same
Can
as
So we
And
need
we are
to
in no
really access the
communication with the
practical
senior to guide
labs
us.
because
Yeah.
yes, sir.
Okay.
Because
Anyway, we can start the course. I have to just finish this one. We have 10 more slides to go. So I hope all have joined.
Hello,
Okay.
sir.
Yeah.
yes,
Most of-
Yes.
Sir, where can I get the contact of director, sir?
Oh, you can have a directory. You can download from the our website.
Website has a directory in which the top contact is of director.
Yes. So inside that directory, you can get the email address as well as the phone.
Okay, sir. Okay, sir,
Yeah.
I will do.
Yeah. Everybody should write at least 4 or 5 email every day. Then he
yes,
will
sir. If
understand the
do,
problem.
we all don't do anything, then one or two cannot
Yes,
do
sir.
anything.
We have to
Yeah.
come together. Yes, sir.
See,
Then
he cannot deny by lingering all these things. Okay. Every small kids, LKG, UKG schools are open now.
yes, sir. Private college भी सारे
what,
engineering का
what is the main reason, sir? Why is it not opening?
All the government.
What I told you is, if you don't want to solve any issue, you just simply say no. If you don't want to take any responsibility, simply say no.
Yes, sir. कोरोना रीजन वैसा रहे नहीं सर.
नहीं, कोई रीजन नहीं है. बिहार इलेक्शन is over, गुजरात इलेक्शन is over, पंजाब इलेक्शन is over. Where is corona?
Yes, sir. और बंगाल
Yes,
इलेक्शन
Sir,
भी चल रहा
our
है.
elections are still there.
हजारों के
Maybe
भीड़
that
में
is why they
चल रही है.
No. This is totally bullshit.
Sir, our parents are also going to job.
Okay. Anyway, so this discussion will not end up. So just focus on your subject. Okay. Anyway, so
Okay,
what we were discussing. What we were discussing about this one-dimensional problem, and we have considered a nanowire having length L, and the edges we consider this as a infinite potential barrier, and the potential we define for a free particle in that one-dimensional potential box is 0 in that length, and then outside of that length is infinite. Okay. Now you have to write the Schrodinger equation. Okay, so we have the operator, Hamiltonian operator in the left hand side, operating on the wave function. Okay, so now you see we are just writing phi of x, not t is not involved here. Okay, now in the right hand side we are writing this E, which is a constant, and this is the energy of the free particle, and you can write in terms of the kinetic energy term. Okay, so this H is operating on phi. It is giving you eigenvalue E, which is a constant, and the same wave function phi of x. Now since this is one variable, then you can just write this del operator in terms of this second derivative, d2 by dx square phi x, and you can just plug v is 0. Okay, inside this region 0 to L, v is 0, so this term is just 1s, and you can write this 2m this side, h cross at the denominator, and E is there. Okay, so this is the differential, second order differential equation. Okay, now you can take a case, case 1 as E less than 0. You know it is not possible, you have just the kinetic energy term, but since this is a bound case, the particle is in between 0 to L, you can just consider that the energy is less than 0, but whether it is possible or not, we can check it. Okay, so in that case we define this prefactor 2me upon h cross as some rho square term. So now here I am putting mod of E. Okay, so if E is negative, then also this rho is positive. This rho square is positive. Okay, so we have extra sign here, minus sign, because we have considered E as less than 0. Okay, now you can look for the solution of this differential equation.
Hello,
yes,
sir.
yeah.
So when E is negative, then rho will not be defined, na, sir.
Why? No, we are just defining this quantity 2me upon h cross square as rho square. Okay.
Okay,
But
yes, sir.
we have considered E less than
Modulus,
0, so that's why this minus sign is there.
actually, E is in modulus, then it will be positive.
Yeah, rho square is always positive. E is
Yes,
mod
sir.
of E. So, but you have to put one negative sign here because E is negative. Okay, this is coming from this main equation. So, if E is negative, then this negative sign will be here, and then this to be positive number. Okay. So, the solution of this differential equation is a linear combination of this e raised to I rho x and you have e raised to minus I rho x. Now, this will be a sine hyperbolic function. Okay. So,
Excuse me, sir.
yes, tell me.
So solution should be rho x and minus rho x only.
Oh yeah,
I
sorry.
think.
Yeah. That's why this is hyperbolic. Sorry, if I is there, then you have the just a sine or cosine term. Okay, sorry. This should be just rho x and minus rho x. Very true. Thank you. Okay. So hyperbolic function is because you don't have the I part. Okay. Thank you. Okay, so sine hyperbolic rho of x. Okay. When x tends to 0, this is fine. But when x tends to L, this is not 0. So in that case, what is the property of the wave function? It should be vanishes to 0 at the edges. Okay. When you have an infinite potential, so in this region and before this 0, the wave function should not exist because potential is infinite. So wave function at 0 and at L, it should vanish to 0. But in this case, the wave function is not equal to 0 when x tends to L. So it means we cannot have a well-behaved wave function for the considered particle having energy less than 0. So E less than 0 is not possible. Okay. Now, so we have another case E greater than 0. So now you can just write this 2me upon h cross as k square. This is we will know this k as a wave vector. Okay. So now the solution of the second order differential equation, you can simply write here e raised to I kx and e raised to minus I kx. Okay. So then any linear combination of these two solution will be a solution of that differential equation. So you can have sine kx or cos kx, and we have just put two constant a and b, and you can determine this constant with the boundary condition. So what are the boundary condition? At x equal to 0, the wave function at x equal to 0 should be 0, and at x equal to L, the wave function at the L should also be 0. So now if you substitute at x equal to 0, then you have a sine k 0. Okay, so this will be 0, and then you have cos 0 is 1, so b, then it is giving you b should be 0. Okay, so now you have put the second condition at x equal to L. Okay, so now this b is 0. You just forget this solution. So you have a and sine k and L. Okay, so now the coefficient, this should be equal to 0. It means a is a constant, and if you put a as 0, then this will be 0. And sine kl, if this function is 0, then also it is 0. But you cannot take a as 0. Why? If you take a as 0, then this whole term will be just 0. Okay, so a cannot be 0. It means you have to just take the condition when sine of kl is 0. So in that case, the kl should be n times pi, and what is the value of n here? Okay. Now suppose you take n equal to 0, then also you will get this 0, but that is very trivial solution. You always get 0. Okay. Now you can take negative integers, that will also give, but when you take the negative integer, then it will give you some negative value. Okay. So in that case, it is not a good wave function, and then in that case you have to just take n as all positive integers, starting from 1, 2 and so on. Okay. Now if you just take n as a positive integer starting with n, then kl is n times pi, and now you can write the value of k, what we have here, k as square as 2me upon h cross square. So you can just write here a square root of 2me, and here we are giving the index n for this energy. Okay, and we are writing this h cross and l, and in the right hand side you have n pi. Okay, so we are just giving index to the energy, okay, corresponding to the value of n. Okay, so now En will be, just rewrite this in terms of this En, n square pi square h cross square upon 2m l square, and where n start with 1, 2, 3 and so on. So now you can see here you have in the x-axis you have n, in the y-axis you have En, and this follows, if you just plot En versus n, not n square, okay, En versus n, then that will give you a parabola. Okay, and but it will not touch to 0. Okay, this you have to just take this scattered point at the edges. Okay, so note that n equal to 0 is meaningless because it implies phi is 0 and e is 0, which is just a trivial solution if you just substitute this. So the final solution, now we are giving index to this phi n, because you have n here. Okay, so phi nx is a sine n pi x upon l. You can also write this term in terms of En. So a sine square root of 2me En upon h cross times x. Okay, so now if you change the value of n here, then you will get different energy value and different eigenfunction. Okay, so now this is the solution you have. So phi n, the property of the wave function is the phi n and the first derivative should be continuous. Okay, so now if you put n equal to 1, you have this kind of wave function. If you put n equal to 2, you have this kind of wave function. So you have nodes and antinodes. So for n equal to 1, you have just 2 nodes at the edges. If you have n equal to 2, you have 3 nodes, 2 are at the edges and 1 in the middle, and antinodes are there. Okay, so we can also put very small question like how many node and antinodes are there if you have n equal to 4. Okay, so in that case you have to just, for the nodes you just increase by 1, and for antinodes it will be same as the value of n. Okay, so just in case of the ground, the first n equal to 1, you have 1 antinode and 2 nodes. For n equal to 2, you have 2 antinodes and 3 nodes. N equal to 3, you have 3 antinodes and 4 nodes, and so on. Okay, so now we have the solution here. This solution, the wave function, is representing that particular particle which is inside this nanowire of length L. Okay, and if you change the value, so you don't know anything about this A, but with the boundary condition you can calculate the value of A. Okay, so how you can do that? So you know, if you calculate the total probability to find that particle between 0 to L, that should give you 1. Means particle must be there in that nanowire. Okay. So you just integrate from minus infinity to plus infinity phi n square dx, and you substitute the phi n value of phi n here. So it will be a square, and outside of 0 to L you don't have the wave function. So you have to write from 0 to L only, and you have sine square n pi x upon L dx, and that should give you 1. Okay. So particle must be there. So total probability is 1. Now if you this is a definite integral, so it will give you some constant value. Then you can find the value of this a square. So a square will be yeah. So you do this simple integration, and then you can show that the a will be square root of 2 over L. Okay. So now you know the solution. So only a was missing. So a, you know, this is the square root of 2 over L. Now you can put the value of n, and then you can get any excited state. This is the ground state. You have the excited state here, 2, 3, 4, and so on. And suppose the particle is excited to some state, suppose 2, and when it goes back to state 1, then it will radiate some energy. Okay, and corresponding to that, you will get some photons having some wavelength. Okay, so you can calculate those properties. So now I will just
Excuse me, sir.
yes, yeah,
Sir, that above graph, can you show?
yeah.
Yes, sir. In that you are increasing, as n is increasing, the graph is shifting upwards.
Yeah.
This will happen really.
No. This is just a representation. Okay, everything is 1D. Okay, this is just representing the wave function. Okay, of that particular particle which is in this rod. Okay, nanowire. It is not like it is going above this thing. So it's just inside the nanowire. Okay. This is just a representation of that particle having some energy, excited state of the levels. Okay. Is it okay?
Okay, sir.
Understand? Okay. Now I will just show you some examples or numerical problems where you can solve and do some practice. Okay, so the question 1, the probability to find, can you see this?
Yes, sir.
Yes, sir.
Yeah, so probability to find an electron in the range x equal to 0 to 3a by 4 in an infinite square potential well of width a is 75%. So it is given to you that probability is 75% between 0 to 3a by 4, and total length of the wire is a. Okay. Now you have to find out the lowest quantum state of the electron. So you have to just find the value of n. So how you can do? Can you try? Maybe you just take 2 minutes. So how you can write this? So in the left hand side, for the probability, you can write this the wave function. Okay, and in integration from 0 to 3a by 4, you have mod phi n square. So you have 2 by a sine square n pi x by a and dx integral 0 to 3a by 4, and that should give you in the right hand side as 3 by 4 the probability. Okay, so now you can find out the value of n from that given Now, if you just consider the second question here, an electron is trapped in one-dimensional infinite potential well of length 2 nanometer. Okay,
Hello,
so
sir.
yes.
So can you say once again solution of question 1? What we have to do?
Okay, so in the left hand side, how you will write? You have to write that integral 0 to 3a by 4. Okay, that is given to you. So 0 to 3a by 4, and then you have mod phi n square. So what is the mod phi n? Is just square root of 2 over a sine n pi x by a, and then you have to take mod square. So that will give you 2 by a sine square n pi x by a, and then you have to do the integral with dx, and limit is 0 to 3a by 4. And in the right hand side, what is given? That the probability of finding this electron in this region is 3 by 4. Okay, 75%. So now only n is unknown, then you can find the value of n. The lowest value of n you have to find out. Okay,
So our answer is 2.
you just do that. Okay, I have not done this integral, so you just do that integral and you will find the value of n. Yeah, you may be right. Yeah. Second question. So you have an electron which is trapped in 1D potential well, and the length of that nanowire is just 2 nanometer. And the question is, can you find the longest wavelength of the photon emitted by this electron as it changes the energy level in the well? So now, when you write the energy, so you have E equal to h nu, and you can convert this hc upon lambda. Okay. Now for when there is a transition, so go back to the this one. Okay. So when you have a transition from second to first level, because energy is inversely proportional to lambda, then the lambda, we are just asking maximum wavelength. When they are doing this kind of transition, then you have to find out the longest wavelength. In that case, En should be smaller. Okay, so what are the value of n you can choose to find out the longest wavelength? So definitely you have to choose 2 to 1. Okay, when they are having a transition from second level to the first level, then that will give you the longest wavelength. Okay, so now you just plug in those value and then find out delta E between E2 minus E1, and that will give you the longest wavelength. You can calculate that. Okay. Okay, so now okay, another problem. This is very important problem. Okay. So what is given here? You have a wave function which is in region x greater than 0 and 0 when x is less than 0. Okay. So the wave function is given as a times x e raised to minus alpha x. Okay. Now question is, you have to find the value of a. You have to find the expectation value of position x and x square. You have to write this wave function in momentum space. Okay, and use this momentum space to find out the expectation value of p and p square. And once you know x square expectation value of p, expectation value of p, and expectation value of p square, you can easily find delta x and delta p. And then you have to show that the multiple of these two, delta x and delta p, must be greater than or equal to h cross by 2. Okay. So now here I'm just discussing this solution. Okay. Let me just put it there. Okay. So just by normalizing, just take the mod psi x square, that will be 1. So given wave function is there, and then you find out the value of a, then a will be like this. To find the expectation value of x, you have to just plug in the value of x in between this pi star and psi star and psi. So this will be your integral, and then you find out.
Sir.
Yeah. Tell me.
Sir, before we took normalization constant as two values, means we generally consider the positive value only. Means here we are considering plus minus.
Yes. So that we have discussed in the when we write the solution of the particle in one-dimensional box. Okay. So A, we have seen that A is greater than 0. Okay.
So only one solution will be there, no? Means plus.
Yeah. So you have to just take out this negative sign. So this is A squares, but we have to take this positive value of this number. Okay.
Okay, sir.
So now you can find the expectation value of x and x square by just plugging this x in between this wave function psi star and psi, and do this integral. You will find this one. Now to write the wave function in momentum space, what you have to do, you have to write the normalization constant as this one, 1 over square root of 2 pi h cross, and the integral, and you have to write the psi of x and e raised to minus ipx upon h cross, and do this integral with respect to x. Okay, so you will get the value like this. Okay. So if you want to calculate the expectation value of p and p square, just write these things. You get this is simple integration, and you people are very smart doing this calculation of integral. So you can work on that, and you can finally show that delta x and delta p is greater than is coming out to be a square root of 3 h cross upon 2, which is greater than h cross by 2. So your whole calculation is right if you get the uncertainty product as greater than h cross by 2. Okay.
Excuse me, sir.
Yes.
Sir, there in first line,
Yeah.
Normalizing the wave function line.
Yeah.
After, sir, a square by 8a cube into gamma 3 should be there. I think you have written.
Yeah. Gamma. So the value of gamma 3. Okay. Oh, sorry. Okay. This is a square root. This is a gamma function. Yeah, you are right. This is a gamma function 3. Okay. So the value of this gamma function 3 is just 2 factorial. So you have this one. Okay. Thank you. So we will just correct this one. Okay. Another question you can just think of, you have given a width of the 1D infinite square well put in. So far we have just discussed about the infinite potential. Okay, we have not discussed any finite one. That is not in your course. So maybe if you are interested for higher quantum mechanics course, then you can read those finite potential barrier or finite potential well, or different kind of asymmetry and so on. But we are not going to discuss. We have just taken a very simple example of infinite potential well. Okay. This is given, the width is given to you as a 2.75 angstrom, and question is estimate the energy of the first excited state of the electron trapped in the potential. So now you have to just read the question once again. We are asking first excited state, not the ground state. So n, we are asking n equal to 2, not the value of n as 1. Okay. So first excited state means n equal to 2. So now we know the expression for En. You have n square, h cross square, pi square upon 2ml square. You have to just substitute the value of n as 2. So E2 you will get like this. Okay. So these are the simple questions we can ask in the exam, and you have to prepare well to answer this type of question. Okay. Okay, now coming back to, so once you know the solution, then you can use the probability information to find out any unknown. If the particle are excited to any different level, then you can calculate the corresponding energy value, and that should be a discrete. We have shown the graph that how energy is changing with n, and if they are de-exciting to the different level, then that will generate some or transmit some photons, and corresponding to that you can calculate the wavelength of the photon. Okay. Now, if you can take any two solutions, suppose n and m, okay, then in that case you can write this as the integral between 0 to L phi n star and phi m of x dx. That will give you a chronicle delta. Means when m and n are same, then only you have value, otherwise it will give you 0. You can also prove this thing just taking n and m like this. So you have a sine of these things and a sine of m pi x upon L. So this will be a square. So this is 2 by L. Now you have sine n pi x upon L and sine m pi x upon L. Now if you just do this integral, you will get this kind of term. Now when n not equal to m, you will get always 0. Okay. When n equal to 1, you will get just 1. Okay. So what is the message here? Each wave function corresponding to different eigenvalue are orthogonal. Okay. So the full solution you can write. So we have n equal to 1, 2 and so on. So any linear combination of those solutions will be the full solution of the particle. So psi of x is, now here we are using discrete, the summation we are using, not integral. So all values are not included. Only n equal to 1, 2, not fractional value is included in this one. So only the discrete value is included, and n starting from 1 to infinity you have. So here is summation over an phi n we are writing. Okay. So you can write in the order of these things. You can find the value of n for a particular nth state by doing this integral. So now we have so far not taken the solution for the time part. So t of t was not included, but once we write the full solution of the particle, then you have to include the functionality of the t. So psi x t will be the solution for the x, and then you have solution for the time part. Okay. So now you have an phi n x and you have e raised to minus I h cross e n t. Okay. So you can find the probability density by just taking the mod of psi square. That should give you 1. So now probability for nth state will be just 2 by L sine square n pi x by L. So I gave you one problem where the probability between 0 to 3a by 4 is 75%. Then you have to just plug in this value in this integral between 0 to 3a by 4, and the probability here in the right hand side is just 3 by 4. So if you do the integral, you will get the answer for n. Okay. Now about the expectation value. So if you know the wave function, then you can find the expectation value of any observable, either position, momentum, or energy, or kinetic energy. Okay. So if you want to find the expectation value of the Hamiltonian, okay, so you have to plug in this operator in between the psi star and psi, and we know this h, how you writing this psi as a summation of a n phi n. Okay. Now this is a constant, so this will just come out, and if h is operating on phi n, that will give you En. Okay. So En, and you know the property of this psi and phi n. So when psi is similar to phi n, then only you will have some solution, otherwise this integral will be 0. So this whole integral will be en mod n square. Okay, so this is very important relation, and we will ask at least one question from this relation. So don't forget this one. So now you can see the expectation value, or this is totally different than the taking some mean value. Okay, when you take the mean value, suppose you have n data set, then what you do? You just sum all those and divide by n. Okay, but here you see here what you have. You have summation of en and an. So you have the weightage of this particular state. So probability is multiplied for every state to take the expectation value. In the denominator, you have always 1. So total probability is 1. So you don't have to write that. So this is totally different than the average value. Understand this? Hello? Hello?
Yes, sir.
Yes, sir. Yes.
Yeah. So this is
Yes.
very important relation. You have to understand this. Okay.
Sir, it is similar to total probability and Bayes theorem, I think.
Yeah. Yes. Any doubt?
No, sir.
Okay. Okay. So let's move on. So now suppose if you take the momentum eigenfunction for a free particle, then how you write? So momentum operator operating on the momentum eigenfunction, which is I am representing here u of p. Then it is giving you some eigenvalue p, the momentum you will get. So this is the same eigenfunction you have. Now the operator for the momentum, you have minus ih cross del over del x. Now you can write this full derivative because yes, you are working in 1D, you don't have to take the partial one. So you can write this first derivative and then you will just plug in this IPH and so on. So the solution will be of this differential equation is C some constant and e raised to IP upon h cross times x. Okay, now you can find the value of C by just normalizing this Bayes function. That will be going to give you 1 total probability. So the value of C will be just 1 over a square root of 2 pi h cross, and this will be, if you just plug in, then that will give you a delta function. So this function has only value 1 when p is equal to p prime. Okay, so now this wave function corresponding to the momentum eigenfunction that is giving you a delta function as p minus p prime, and when these two are equal, then only you have the sum value 1, otherwise it will be a 0. Okay, so now you can just start with this momentum function, eigenfunction. Now you can write, suppose you just take the same eigenfunction which was we have used for the energy eigenfunction. Okay, so here we are just taking momentum eigenfunction as energy eigenfunction, and then we will see these two are not same. Okay, so now if you just substitute this, then you have operator for p operator, then you can just write this minus ih cross del over del x or d over dx, and then phi n x we are just writing. We are just taking energy eigenfunction as momentum eigenfunction. Okay, here then you can see this is not equal to. So you can see here. So this should give you the same function. So what you have when the operator is operating on a wave function, that will give you some eigenvalue and the same wave function. But here you can see this function is changed sine to cos. So this is no longer the same wave function. So it is not equal to the eigenvalue of this operator Pn, and it is not the same wave function phi n. Okay, so this problem is because E is directly proportional to P square, so you can have plus minus P as a solution for this E. Okay, then you can express this sine theta, whatever you have the solution here for the wave function. Okay, in terms of square root of 2 by L, and then you have sine n pi x upon L. So you can write the sine theta in terms of this exponential term e I theta minus e raised to minus I theta by 2i, and then you can define phi plus and phi minus, and then you operate on phi plus, then you will get the momentum eigenfunction for eigenvalue of this operator and eigenvalue of this operator. So you can resolve this problem by taking this kind of function for the momentum eigenfunction. Okay, so energy eigenfunction is not same as the momentum eigenfunction. Now what we learned so far, energy levels increases as the square of the integers n. Okay, if you just see the graph E versus n, it is a parabola but not touching this 0, n equal to 0 is not allowed. The wavelength of the standing wave, de Broglie wave, for the nth harmonic is, you can write in terms of lambda, so L equal to n lambda n upon 2, just like if you see the this graph. So you have L by 2 here, lambda by 2. Here you have the length is fixed. So how many wavelength you can have for any excited state, you can write in terms of lambda. So L you can write n times lambda n by 2, and corresponding momentum you can write for the nth state as h over lambda by n, lambda n. We have already seen the equation for energy, n square. Here we are just writing h, not h cross. So h square upon 8 m L square. Don't worry about this change in expression. So because there you had h cross square, pi square was there. Okay, so this is the same expression you have. So what we learned through this example, a trapped particle cannot have any arbitrary energy, whereas a free particle can have any energy value. Okay, so this is totally different result than the classical physics, where if we have a free particle, all energy are allowed, acceptable, but in the quantum physics, when these are bounded, so when you go from the macromolecule to very, very fine nanoparticles, then these discreteness of energy levels come into the picture. Okay, so this is totally different than the classical behavior of the particle when it is in the nano regime. Okay, so the trapped particle have discrete energy levels. A trapped particle cannot have zero energy. We have also seen that n equal to 0 is not allowed. So the trapped particle must have at least some kinetic energy. This is very different from the classical physics, where all non-negative energy, including 0, are allowed. Okay, the Planck constant h is very small. That's why you have the order of 10 raised to minus 34 in the SI unit, and then so it is very difficult to realize the quantum effect for a macromolecule. So you can, if you calculate the wavelength for a massive particle, then you will see the number is quite different, and you cannot observe those wavelengths. Now, this is very important problem, but we will not going to ask any. In the physical examination, we can ask this type of question, but online numerical example, we cannot have the facility to ask this kind of question. Suppose you shift the box, so length is same, 0 to L. Okay, length is L. Now we just shift the problem, like place the nanowire between minus L by 2 to L by 2. So how you define the wave function? So wave function, you know the solution, phi n of x square root of 2 over L sine n pi x upon L. But here we have shifted this. So same thing should reflect here, x minus L by 2. Now this should be a well-behaved wave function, Means at x equal to minus L by 2 and at x equal to L by 2, the wave function should vanish. Wave function should be 0 because you have infinite potential at the edges. So wave function cannot go into the infinite potential regime. Okay, so you have to just subtract this x minus L by 2 to have the similar wave function to represent the particle trapped in a nanowire of length L. Okay, so now you will get two different kind of solution for n. So if you combine these two, then you will get n equal to 1 to infinity. But here you can have odd and even wave functions. Okay, so this will give you n equal to 2, 4, and 6, and this cost will give you 1, 3, 5, and so on. Okay. Now you can extend this idea to three-dimensional box. Now so far we have done a simple problem of particle trapped in one-dimensional box. Okay, so now here we have taken a cube of length L. So you have L, L, and L, L, E, H. Okay, so now again we are considering a free particle is in the cube. So if we talk about a free particle, then only we have kinetic energy, no potential energy. So V of xyz is 0 here. Now you have to write the Schrodinger equation for this particle, which is in cube. So Schrodinger equation, you have to write the Hamiltonian, where only kinetic energy term is there, no potential energy term, and then you have the wave function, which is now depending on x, y, z, and t. So, and in the right hand side you will get the energy and then the same wave function. So you can separate the wave function in terms of the position and the time. So we know exactly the solution for 1D problem. So you have now three direction x, y, and z. So that will be you having a product of all these three function, and this constant is there. You can determine this constant by using the boundary condition. Okay, and t will be again same. So this is not going to change. So En is very important relation. You have h cross or h square at m L square. Now here you have nx square, ny square, nz square. You can come back to the same relation when you just omit y and z component, then it will be just n square in one dimension. Okay. So now for ground state, you have just one state, which is non-degenerate. Okay. If you put n equal to 3, then n equal to 2, then how you can choose nx square, ny square, and nz square, so that you can get n equal to 2. Okay, so you can take 1, 1, 0, or any alternative of this. So you will get three different combination to get the same energy value. So you can vary nx, ny, nz to get the total value as this n equal to 2, corresponding to E2. So degeneracy of that second state is 3. Degeneracy of the third state is 5, and so on. Okay. So we can ask very simple question: what are the combination you can have for second energy state, third energy state, and so on. Okay. So if you have just one solution for a given eigenvalue, then that is called non-degenerate state, and if you have more than one solution for a given eigenvalue, then you have degeneracy. So this is all about the one-dimensional potential problem.
Excuse me, sir.
Yeah, tell me.